Good morning, everyone. It's a pleasure to be here. My name is Alexander Marchena, and I'm here to deduce and talk about diffusion equations about having in count cylindrical coordinates. Okay, let's start. Okay, this topic is so important in the industry because we have many different uh, factories, industries, like for example, sugar industries, petroleum industries, oil and gas industries, and many other ones. And we have pipings, and we have many different equips which are composed about pipes, about bulbs, etc. But in many cases, we usually use cylindrical pipes. And when we are talking about cylindrical pipes, we are talking about cylinder. Okay, so there are many manners to make a deduction of height diffusion equations about Cartesians or maybe cylindricals or maybe spherical coordinates. But in this case, I'm going to introduce to you cylindrical coordinates. Okay, so in this case, we can use this equation when we're talking about heat exchangers, when we're talking about thermal insolution pipelines, when we talk about electric cable boring, chemical reactors with tubular structures, evaporators, and sugar factories. Okay, so our goal is to derive the heat diffusion equations for system helping understand and predict temperature distribution over time and space. In this figure one, we have a cylinder. We have a cylinder, and we have some elements about it. Okay, we have a volume element, which is selecting with a red cursor red. We have a radio R, a radio denominated by the letter R, and a radio is denominated with R plus delta R. Okay, so we have a very complete cylinder array over here. So let's continue. Our objectives are to derive the general heat equations in cylindrical coordinates, explain the physical meaning of each term, introduce the concept of thermal diffusivity, and provide a comparison of diffusivity across solids, liquids, and gases. Okay, let's start with a control volume. In this kind, we have an entire cylinder, and this in the other in the figure two we have a cylinder, but with a control volume. Okay, we have three representations about the same thing. That is control volume. And in the left side we have a cylinder, and we were selectionate a little portion of that cylinder. Okay, so in this kind we have this portion in a plane Cartesian, in a Cartesian plane, in which we have c axis, y axis, and z axis. Okay, and we are going to make a zoom on this parallelepiped rows, and we have this one, right? This one. In this case, we have three axes: two x c x x n and x theta. Okay, and we have a volume concept, and we are making some introduction to calor, to heat. Okay, we have a QR, which is the rate of heat which is going into an Rx. We have a QC, is the heat which is inlet in a CX, and we have the Q theta, which is the heat which inlet in the theta x. Okay, so we're gonna use these three figures to understand what can we deduce the conductive cylindrical coordinates equation. Okay, let's continue. We have some assumptions to derive the following equation, right? We have some assumptions, and we have to energy balance. But let's see first the assumption. To derive the equations of cylindrical coordinates diffusion, we have continuum hypothesis, that is meaning temperature is continuum function. We have to homogeneous and isotropic material, that is all the properties of materials is the same in all the volume of the material. We have a constant thermophysical properties like conductivity, specific mass or density, and Cp is heat, specific heat, constant pressure. Okay. We have to that we are talking about not fluid motion. There are no motion of the fluid. Okay, we are in a poor conduction, and maybe some heat generation may be present. Okay. Okay, in this line, we're going to talk about the energy balance. Okay, we have uh, a rate of conduction minus rate of conduction, but in the other side of the volume control, plus a little bit generation of heat. We all these operations are going to be to us a rate of change of energy. Okay, so let's continue. We have here some equations which is deduced about this volume control. Okay, this control volume we have, as I was explained a few minutes ago, we have three x's: x is q theta, qr, and qc. Okay, so now we are going to talk about heat conduction in radial direction. Okay, the radial direction are qr, and so since Fourier's law, we have in that QR the following equation. We have QR is equal to minus K for a gradient of temperature about radium. Okay, so here we have in air in the next part we have that the Q inlet, we have this minus K times delta T and delta R apart. Okay, this R we are going to multiply it by delta T. That is the super force that will inlet the flux of heat. Okay, we have to in the other side and around here we have R mark dr. This is passing the volume control, and we have something like this, something like before. Okay, so we have the Q out, the heat outlet. We have a minus K for delta T and delta R. But we don't just analyze here in R, but we are analyzing R mass delta R. That is passing the volume of control. Okay, and so on. We have the net flow radial, that is the resting, no? Q out minus Q in, and we have this equation we are going to present here. Okay, delta QR is a variation about air of K air in gradient of temperature about air with this area. Okay, so let's continue. This is in the X part. Now in the X theta, okay, we have the following ones. In the X theta, the same thing as before, the same thing. We have a Q theta in Fourier laws. We have minus K, but one R delta T and delta theta, we are talking about theta. No? Theta is here, right over here. We have inlet Q theta and outlet Q theta plus delta theta plus delta T. Okay, so now we have net conduction in theta. In conduction of theta, we have a delta as before. Delta theta is a variation about theta of K for a gradient of temperature, but this time is about theta for an area. Okay, for an area. Oh, look at this. We have an area here, in this case here, we have an area which is not a rectangle. This area has a curvature, and because of that, we have to part it or R. Okay, so in this case of here, we have a rectangle. So here we have an area which is the multiplicate this longitude, but by this one. Okay, so this is the balance of the conduction in angular direction, no? In the angle. Okay, now we're going to heat conduction in axial direction. What is the C direction, the C axis, okay, which is right over here. We have a same thing, okay, Fourier's law, which is inlet a flux of heat, and we have an outlet of flux of C mass delta C, okay, and the same thing we have this equation which is in here, okay. As we can see, we have here a second derivative right over here, in actual direction, in angle direction, we have second derivatives, okay? So let's take account of this. Now, for the last one, we have an internal heat generation. No, maybe it's a generation which is generated right inlet of this volume of control. So we have internal generation represented by Qn. It is equal to Q, but a little portion of volume which is over here, okay? So the accumulation will be density, height specific height, pressure constants, and a gradient of temperature about time, okay? And we have multiplied that bit by a volume of control, okay? So if we sum these equations by plus this equation, plus this equation, plus this equation, we are going to have this equation from here. This equation of here is the finite heat diffusion and cylinder coordinates equations, okay? We have all the terms here. Now, there is a pair, an alpha. Alpha is a term which is named thermal diffusivity, okay? But what is thermal diffusivity? As my own words, I can define thermal diffusivity like measures how quickly a material reacts to change in temperature, okay? This is for example, we have a longitude for metal, and in one line, in one side or place of this metal is so hot, we have a law relation which that that's that hot part of that metal is going to diffusing to the cold side. So we are talking about of this property of this material about thermal diffusivity, okay? So there are many materials, many matter materials. We have solids, liquids, and gases. In this case, we have a solid, which has electrons carry heat efficiency much better than molecules bumping into each other. We have the repulsion forces are lower than attractive forces. In the solid, we have more attractive forces in the molecules. And another property is the thermal conductivity is high. That is a consequence of behind, which the molecules are together. There are more conductivity, and consequence, we have a thermal conductivity high, okay? And another character of solids are the density and high capacity are moderate, okay? Okay, and in the case of liquids, we have no free electrons, no valence electrons, we don't have it. And for consequence, we have it moves only through molecular vibration and collision, okay? Much lower conductivity. That's because in the liquid we have the repulsion forces. The repulsion forces are equal to the attractive forces, and we have an equilibrium right over here, and that's because solids are better have very conductivity than liquids. Okay, so we have many different things or topics like over here. And what about the gases? The gases and the molecules, the repulsion force are more separated. Molecules are more separated. That's because the repulsion force predominates to the attractive force. And because of that, gases are not very good conductivity has. Okay, so a conductivity is also low, but intensity is super low. That improves diffusivity a bit. Okay, so that's really consequent, right? Because if the density low a little bit of the gases, we have to tend to a case is a condensate a little bit of them. Okay, so that's because the density improves a diffusivity in a little bit. Okay. Okay, to finalize, we have this form. This form is the thermal coefficient, okay, thermal diffusivity coefficient, which is alpha. And we have to some deductions. For example, in metals, we have high conductivity and moderate this product of the denominator, and we are going to have a high diffusivity. And we in the liquids ones, if we have low K, we are going to high this one high, and we are going to have a low diffusivity. And in the case of the gases, we have low K and very low this one too. We have moderate diffusivity. So this is a simple analysis about this formula. Okay? And to conclude, we can say that in this presentation, we derive the heat diffusion equation in a cylindrical. This is so important. A crucial model for analyzing radial heat conduction in systems like pipes, reactors, and insulation layers. Starting from a physically defined control volume, and we apply many different equations like conservation, like energy conservation or Fourier's law to get the second order equations about diffusivity in a cylindrical coordinate. And we find the thermal diffusivity as alpha. Alpha links how fast a material conducts heat and how much energy it stores. We discussed many different physical meaning about solids, liquids, and gases, and we have some deductions about this kind of materials. Okay, so in this case, I want to thank you very much, and it's all for today. Thank you very much.